As we previously stated, theoretically combustion in the gas turbine engine occurs at a constant pressure. This is achieved partly through the continuous process of the Brayton cycle, and also by the fact that the combustion chamber is not an enclosed space. These circumstances ensure that there are no fluctuations of pressure in the engine as there are in the piston engine, where peak pressures greater than 1,000 pounds per square inch have to be accommodated. These high internal pressures necessitate utilizing extremely strong and heavy construction in the piston engine, and also, if detonation is to be avoided, the use of high-octane fuels. In contrast, in the gas turbine engine, the use of low-octane fuels and relatively light construction methods are the rule, rather than the exception. The turbojet is a heat engine. The higher the temperature attained in combustion, the greater the expansion of the gases, and hence the greater efficiency of the engine. There is, however, a limit to the amount of heat that can be released into the turbine from combustion. This limit is imposed by the materials from which we manufacture the nozzle guide vanes and the turbine blades. The Germans' inability to produce materials which could withstand the heat of the gas stream was the main problem with the early German gas turbine engines. Because of the poor materials used in the turbine assemblies, the engines would only run for between 10 to 20 hours before the turbine blades suffered meltdown and engine disintegration commenced, usually in a quite catastrophic fashion. The use of modern materials and extremely efficient cooling methods in the nozzle guide vanes and the turbine blades has enabled the use of much higher gas temperatures in the latest engines. This has resulted in the more modern engines having a higher thermal efficiency than their predecessors. Gases behave differently from the other two commonly studied states of matter, solids and liquids, so we have different methods for treating gases and understanding how they behave under certain conditions. Gases, unlike solids and liquids, have neither fixed volume nor shape. They are moulded entirely by the container in which they are held. There are three variables by which we can measure gases: volume, pressure, and temperature. We'll discuss two of the so-called gas laws which are most pertinent to the operation of the gas turbine engine: Boyle's law and Charles' law. Robert Boyle was born in 1627 in Ireland. He made important contributions to physics and chemistry, but is best known for the law which was named after him, concerning an ideal gas. Boyle's law states that, in a gas which is held at a constant temperature, the volume of that gas is inversely proportional to its pressure, or pressure times the volume equals a constant. This holds true where P is the absolute pressure of the gas, and V is the volume occupied when the pressure is P. This is a reproduction of an experiment carried out by Boyle. He had a calibrated syringe filled with air and deduced its volume. While taking care to retain the temperature of the air inside the syringe constant, he increased the pressure and decreased the volume inside it by placing weights on its plunger, taking readings as he did so. You can see that by multiplying the volume by the pressure, the answer remains a constant. Hence, the product of the absolute pressure and volume of a given quantity of gas is constant, as long as the temperature of the gas does not change. Try moving the plunger up and down yourself to simulate changing the weight on it, and note that the results of P times V always remain a constant. Because of the interest in hot air balloons in the early 1800s in France, Jacques Charles and Joseph-Louis Gay-Lussac made detailed measurements on how the volume of a gas was affected by its temperature. Just as Robert Boyle made efforts to keep all properties of the gas constant, except for the pressure and volume, so Jacques Charles took care to keep all properties of the gas constant, except for its temperature and volume. Charles' law, or Gay-Lussac's law, states that if any gas is held at a constant pressure, its volume is directly proportional to the absolute temperature. Or, if stated as a formula, the volume divided by the temperature is a constant. Just as we did to demonstrate Boyle's law, we'll replicate an experiment similar to one carried out by Jacques Charles. If we partially fill a calibrated syringe with air and place it in a container of water, then by increasing or decreasing the temperature of the water, and thus increasing or decreasing the temperature of the air inside the syringe, while taking readings of the volume and temperature, and then dividing volume by temperature in degrees Kelvin, we see that the answer is a constant. Remember that, in theory, the pressure inside the syringe remains constant also. Try changing the temperature of the water for yourself, and notice that the results of the volume divided by the temperature remain a constant. Although both Boyle's law and Charles' law work in theory, we are unable, with existing technology, to make them work in practice. For instance, it's impossible as yet to increase the pressure of a gas without increasing its temperature, because of the adiabatic heating which inevitably occurs. Remember the example which is consistently quoted of how a bicycle pump always heats up when air is pumped into a tire. By using Boyle's and Charles' law together, we get a practical method of determining what is happening to the gases inside the gas turbine engine, where temperatures, pressure, and volume are all changing constantly. With the scientists' usual lack of imagination, they have named the integrated Boyle's and Charles' law the combined gas law. The combined gas law represents the relationship between volume, pressure, and temperature. This may be shown as P1 times V1 over T1 equals P2 times V2 over T2. The three main stages when these conditions change in the gas turbine engine are during compression, combustion, and expansion. During compression, work is done to increase the pressure and decrease the volume of the air. There is a corresponding rise in its temperature. Just as they do in the piston engine, higher compression ratios give higher thermal efficiency and lower specific fuel consumption. Notice that the velocity of the air as it progresses through the compressor is actually reducing. This is required so that when it gets to the combustion chambers, its speed is not such that it will extinguish the flame. During combustion, the addition of fuel to burn with the air increases the temperature, and there is a corresponding rise in its volume at an almost constant pressure. The velocity of the gas flow continues to reduce through the combustion phase, until the end of the combustion chamber, which, due to its convergent shape, initiates an increase in its value. The reason for this will soon become apparent. During expansion, when some of the energy in the gas stream is being converted to mechanical energy by the turbine, there is a decrease in both the pressure and the temperature of the gas with a corresponding increase in its volume. The changes in velocity over the expansion phase are a little more complicated than in the previous phases. The expansion phase is when the kinetic, pressure, and heat energy in the gas stream are being converted into mechanical energy by the turbine to drive the compressor. The turbine is most efficient at converting the kinetic energy in the gas stream into mechanical energy, and in order to do this, the nozzle guide vanes which precede each turbine rotor stage are shaped to form convergent ducts. At the nozzle guide vane stage, the pressure energy, and to a lesser extent the heat energy, are reduced by the convergent ducts, and converted into kinetic energy, which, as you can see, shows a dramatic rise. The turbine rotor following each nozzle guide vane stage reduces this kinetic energy by converting it, and some of the remaining pressure and heat energy, into mechanical energy. Succeeding nozzle guide vane stages will continue to convert the pressure and heat energy in the gas stream into kinetic energy, and the turbine rotor stages which follow them will convert that kinetic energy into mechanical energy. The gas stream is then directed into the exhaust nozzle, where the velocity decreases at the expense of a small rise in pressure. This decrease in velocity assists in maintaining the losses in the jet pipe due to turbulence at a minimal level. Finally, as the gas passes through the sharply convergent propelling nozzle, the duct shape causes a distinct increase of velocity, and the pressure of the stream drops to that of ambient in response to that increase.